Hi, my name is Jossie Kluger.
My name is Maha Haji, and today we'll be discussing the work we've been doing in optimizing a symbiotic wind wave storage farm for cost and load matching. This work is done also in collaboration with Professor Alex Slocum. Wind turbine technology has evolved over the years from onshore wind farms to commercial fixed bottom offshore wind farms to floating platform concepts, which are being tested at the prototype and small farm stages. Shown here and from the left to right are pictures of each of these different technologies. Offshore wind is promising because their wind is stronger, steadier, and there's plenty of space. However, it's much more costly the further offshore you go. When ocean depths exceed 60 meters, fixed bottom wind turbines are no longer economically feasible. It is estimated that 80% of the world's available offshore wind resources are located in these deeper waters in depths of greater than 60 meters. Shown on the bottom is the levelized cost of electricity for each of these different types of wind turbine technologies in dollars per kilowatt hour. Most of the cost difference between fixed and floating wind turbines can be attributed to two main factors. The floating platform is almost twice as expensive as the fixed bottom structure, and floating farms tend to be located farther distance from shore, which increases the cost of the electrical infrastructure. Another challenge with wind power is its volatility and low predictability. This is problematic for operating electric grids with a large amount of wind power. Here we generated a plot of normalized wind power data based on a standard wind turbine curve and hourly wind speeds recorded by the NOAA buoy 46022, which is located 17 nautical miles southwest of Eureka, California, shown in the map on the left. Additionally, we've included normalized hourly electricity demand on the plot using information from the California Independent System Operator, CAES database. In the figure on the right, we see a snapshot of the predicted normalized wind power produced over a 5-day segment in the winter. We also see the normalized electric grid power demand in this region. As you can see, the wind power supply is much more volatile than the power demand. This trend persists throughout the year, as shown here for the spring season, as well as the summer and fall seasons. This indicates that there exists a supply-demand matching challenge. As more wind power and other renewables are added to the grid, more energy storage is required to match the supply with the demand. Several features of wave power suggest that adding it to a floating wind farm can help decrease the cost of offshore renewable power. First, previous studies have shown that attaching a wave energy converter to a floating wind turbine can stabilize the floating wind turbine platform. Even when unattached, the wave energy converter can shield the floating wind turbine from waves. This figure shows a combined offshore wind wave farm that leverages this shielding effect. If the wave energy converter decreases the structural loads on the platform and tower, then these components can be redesigned with less steel, which decreases their cost. Second, stabilizing the platform, particularly with pitch motion, can improve wind turbine power performance since it reduces turbine interaction with its wake. Adding wave power to a farm can make more efficient use of electrical infrastructure as well. Third, wave power tends to be smoother and more predictable than wind power, so it helps integrate the renewable power with the electric grid and match demand. For our study, we wanted to further investigate these effects. We considered an offshore wind farm with standalone floating wind turbines, standalone wave energy converters, and combined systems. The wind turbine is rated for 6 megawatts and uses a deep draft cylindrical spar platform. The wave energy converter is rated for 290 kilowatts, and it is a two-body point absorber designed by the National Renewable Energy Lab, or NREL, where a float moves relative to a reference body. The power is then generated through this relative motion. In the combined system, the existing floating wind turbine platform is the reference body for the wave energy converter float. The combined systems can have synergistic mechanical performance. This plot compares the annual response statistics of a standalone floating wind turbine and wave energy converter with a combined system. The combined system has a larger relative velocity between the float and reference platform. This corresponds to more harvested power since the system harvests power from the relative motion. We also see that the platform of the combined system has less surge and pitch motion. As mentioned earlier, this is beneficial for the wind turbine power and structural performance. Finally, unfortunately in this system, coupling between the wave energy converter and floating wind turbine increases motion of the floating wind turbine platform. While floating wind turbine platform heave motion isn't as problematic as pitch motion, future work will investigate floating wind turbine and wave energy converter combined configurations that reduce this motion as well. Historical wind and wave data also indicate that wave power is smoother and more predictable than wind power. In the plot on the right, we have added the normalized predicted power produced by a wave energy converter co-located with the wind turbine off the coast of Eureka, California. Normalized wave power is the red line, and we can see that it changes more gradually compared to the normalized wind power, the blue line. Again, we see this trend persist through different seasons of the year, shown now for spring, as well as summer and fall. Now we take these normalized power fluctuations and scale them to consider a wind waveform with different fractions of power from wind versus wave. This bar plot shows the total harmonic distortion over a 5-day period for an offshore farm with different fractions of wind and wave power. Total harmonic distortion measures the fluctuation in the power normalized by the average power produced. Smaller harmonic distortion is better since it indicates less energy storage is required to match the power supply with the smoother power demand. The leftmost bar shows that the most total harmonic distortion occurs for a farm that is 100% wind power. On the right, increasing the fraction of wave power decreases the distortion. Again, these trends persist through the different seasons of the year. The summer months show the biggest smoothing effects. For our research study, we wanted to quantify the cost benefits of wave power in an offshore wind wave farm. We wanted to look at how the smoother wave power can decrease the energy storage costs needed to match supply with demand. I will now hand the presentation over to Jossie to describe the highlights of these studies.
For our study, we wanted to compare the performance of systems with varying levels of wave power and energy storage to understand the potential advantages of using different levels of wave power. Our investigation considers an electric grid with a 600 megawatt offshore farm comprised of wind and wave power, compressed air energy storage, and a natural gas plant providing required base power to satisfy a power demand with fluctuations based on the historical demand from Eureka, California, recorded in 2017. We considered these two components in an isolated electric grid. Our investigation used two main steps. First, a parameter sweep varies the renewable energy penetration in this grid, the renewable energy distribution between wind and wave power, and the amount of storage power capacity. Second, for each parameter set, an optimization routine considers the hourly energy storage schedule and adjusts the flow to minimize an objective function with three components. We wanted to minimize the cost of operating the storage system, which is proportional to the power flowing through it, minimize the amount of curtailed energy, and minimize the cost of running the gas plant, which we modeled as having a cost for switching on and off and for ramping power up and down. The system is constrained to balance the power supply with demand, and this optimization assumed 100% accurate wind and wave power forecasting. Here are a couple examples of what the results looked like for two different optimized points of the parameter sweep. For both of these examples, we used 100% renewable power penetration and energy storage power capacity equal to 50% of the peak demand. These plots show a 5-day snapshot of the power balance. The blue area is the gas power, the red area is the wind power, the blue line is the sum of the wind, wave, and gas power. The red line is the smooth demand. The purple area shows the power provided or absorbed by the storage system to balance the blue supply line with the red demand line. The top row is for a farm that is 100% wind power. The bottom row is for a farm that is half wind power and half wave power. Comparing these plots, we see a smaller amount of green curtailed power. If we look at 5-day snapshots in the other seasons, we see that this trend generally persists throughout the year. Here we can see the trends in the annual statistics for the optimized parameter sweep. Each column is a different renewable energy penetration level. The y-axis varies the fraction of farm power that is wave power versus wind power, where 0 represents 100% wind power from the farm and 1 represents a farm that is 100% wave power. And the x-axis of this plot varies the power capacity of the storage system, where 1 corresponds to a storage system with a power capacity that matches the peak electric demand. These plots show the annual fraction of renewable energy that is curtailed. And we can see that for a moderate amount of energy storage, a mixture of wind and wave power has less curtailed power than a farm that is solely wind or solely wave power. These trends are more significant as the renewable energy penetration increases. Here, these plots show trends in the annual electric to grid efficiency for the renewable energy farm. This efficiency reflects some transmission losses, which are about 3% for all parameters, and the variations mostly reflect the different amounts of power that flow through the energy storage system. The energy storage system is only 81% efficient when power flows through it. We see that the efficiency of the farm increases as it is comprised of more wave power, and this reflects less power flowing through the storage system. Unfortunately, with current technology, wave power is much more costly than offshore wind power. In these plots, we see that for all renewable energy penetration levels, the levelized cost of energy is lowest for a farm that is 100% wind. And it is more cost effective to add storage to a farm than to add wave power to it. In these plots, we can see that the capital cost of the farm increases much more rapidly when you replace wind power with wave power compared to adding storage capacity. And this trend holds across all renewable energy levels. On the previous slides, we saw that adding wave power decreases the curtailed power and improves the farm to grid efficiency. But here we see that the cost of energy is dominated by the capital cost of the systems. Now, fundamentally, wave power is more costly than wind power because harvesting wave power requires an oscillating mass. Unlike for wind power, harvested wave power is proportional to the system's mass, and oscillating energy converters also suffer from the frequency mistuning power adaptability challenge. If we consider the main components of levelized cost of energy increases for larger capital cost and it decreases for larger energy production. A lot of research has gone into looking at how to increase the energy production, the denominator. Our future research will look at ways to decrease the cost of wave energy converters to improve the cost of energy. We'll look at the numerator. We will consider how to make wave energy converters from repurposed or soft materials rather than rigid metals. To summarize this presentation, we can make several conclusions about wave power. On the structural side, attaching wave energy converters can decrease the stress and motion of floating wind turbines, which improves their cost efficiency while providing additional power from the offshore machine. On the power flow side, we see that adding wave power improves the farm efficiency and reduces the energy curtailment. Future work will further investigate a few different areas. First, it will look at minimizing the steel in the wind turbine and platform. We will also consider different ways of coupling the wave energy converter with the floating wind turbine to further reduce the floating wind turbine motion. We will also look at reducing the wave energy converter cost by considering repurposed or soft structures. Finally, we will consider tuning and expanding the power balance optimization to consider imperfect power forecasting and transmission lines that connect different regions. This is a broad range of areas that can be approached from many different angles, so let us know if you're interested in collaborating on any of them. Again, my name is Jossie Kluger, and my colleague Maha presented the first half of this talk. We did this work with MIT professor Alex Slocum, and thank you very much for your attention.